Hi, my name is Alyssa Murphy, and this is my lab report for Lab 5, the Choose Your Own Adventure Lab for Physics 2211. The purpose of this lab was to model the motion of the bottom of a slinky in free fall, including drag force after it was dropped from rest. The experimental model will then be compared to a computational glow script model. The concepts we'll be reviewing in today's lab is Newton's second law, which states that the net force on an object is equal to the change in momentum over the change in time. In this lab, this principle will be important for updating position and velocity, as well as for calculations for net force acting on the slinky. The equations that will be used today are net force, which F net equals the force of gravity plus the drag force plus the tension force of the slinky. The velocity update formula VF equals VI plus F net over M times delta T. The position update formula RF equals RI plus V average times delta T. Gravitational force will be negative M times G in the Y direction. The tension force will be M times G in the Y direction, positive this time, and the drag force will be the negative magnitude of velocity squared in the direction of the velocity. For a preview of the results, the graphs from the experimental model versus the computational model are similar but not exactly lined up. This is likely due to a number of reasons that will be covered towards the end of the lab report. In this graph, the blue line represents the tracker data and the orange line represents the glow script data. Now, going into the experimental model, the system in this case was the slinky, the surroundings were the earth and the air, and then for the initial conditions, the position was found based on the tracker data to be 0.03470, negative 3.040 meters. The mass was 0.25 kilograms, and the length was 1.29 meters. And then here is the tracker video. And then going into the computational model based off of that experimental model, starting with the creation, for the system mass up here, ball.m was changed to 0.25 kilograms, the actual mass of the slinky, and then that ball position was changed to that initial position of the slinky, the bottom of the slinky, found from the tracker video. The g here is just the magnitude of the acceleration due to gravity, and then this proportionality constant down here for the drag force was found by guessing and checking the computational model with the experimental tracker data. And then in the first calculation loop, I set t to be less than 5.1. 5.1 seconds was when the bottom of the slinky started to just fall by itself versus at the beginning when it's just not falling. So before the slinky starts to fall by itself, the net force is calculated to be a combination of the weight force due to gravity and the tension force in the slinky, which are equal and opposite. And then using the momentum principle, the velocity and position were updated with these formulas here. In the second part of the model, I set t here to be the total overall time from the tracker data. Now, because this is after the bottom of the slinky has started falling, here the net force is going to be the addition of the gravity force and then the drag force from the slinky, which is calculated using these formulas here. And then again, the position and velocity were updated using the typical update formulas. So to go into some error and the results, potential sources of error, the proportionality constant is the biggest source. When calculating the drag force in the second calculation loop, the proportionality constant B is used. And then this value is found by just experimentally, continuously checking the tracker data versus the glow script data, so it's really not an exact number, which is likely what led to the two models having a slightly different steepness. Then the other source of error would be tracker errors. The video that was used for tracking had a lighter background, which sometimes made it difficult to place the tracker exactly where the bottom of the slinky was, especially once the bottom started moving down, which likely led to slight imperfections in the tracker data that made making a perfect computational model difficult. So we can see this again with the graphs. When the data produced by both graphs are compared, the experimental data is more imperfect, this blue line, and it's slightly steeper than the computational data. Again, that steepness is likely due to a difference in the proportionality constant. And then these kind of rigid lines are from the imperfections in the tracking. Thank you very much.